So in this video, we're going to discuss something called the noble gas electron configuration and valence electrons. Now, just so you know, sometimes the noble gas electron configuration is called the valence electron configuration or shorthand configuration, but ultimately they are all the same thing. So just in case you hear those terms or I mess up and call them something else, that's what we're talking about. So we're also going to talk about valence electrons and the role they kind of play in the overall structure of the atom. Now, this should look familiar because we talked about how this right here is an electron configuration where it tells us how the electrons are organized. But the reason I bring it to your attention is that when we look at the S sublevel here, this column right here, that indicates that the S sublevel is filled. Okay, because remember the S sublevel can only hold 2 valence electrons. And if we go over here to what we affectionately called the P block, you notice that it goes 1, 2, 3, 4, 5, and then we get to this 6. And that represents a filled sublevel. Okay, now you'll notice helium doesn't have a P, it's technically an S, but it's still filled, and that's what makes that column significant, is the uppermost, the uppermost sublevel is filled, so it's energetically stable. That is an incredibly important point. Filled sublevels, okay, so filled sublevels are stable sublevel. And that basically tends to explain the function of an atom in terms of chemical reactivity. Now, one thing we need to notice is that once we get to a noble gas, I'm going to change colors here for a moment. Let's go with green. Okay. Once we get to a noble gas, every element after that is basically helium plus that 2s1. Helium plus 2s2. Oh, sorry, that looks really dumb. Helium plus 2p1. Okay? When we get to neon, that's another filled sublevel, so it's significant. The noble gases are significant because they are filled sublevels, which make them stable sublevels. So we can use them kind of as fillers, where this turns into neon plus 3s1 or plus 3s2 for magnesium, or 3s2 plus 3p3. And this will make more sense in a little bit, but essentially what I'm trying to get at is that the configuration for everything after a noble gas is identical up to the noble gas. So sodium has the same core configuration as neon. Aluminum has the same core configuration as neon. Chlorine has the same core configuration as neon. So we don't have to write 1s2, 2s2, 2p6 over and over and over again. We can just write neon and then add the extra stuff on top of it. The nice thing is it allows us to omit a portion of the electron configuration. Okay? And the way this makes sense, let's look at the orbital diagram for sodium. The orbital diagram for sodium is, I'm going to switch back to red. Okay? We've got 1s2, 2s2, 2p6, 3s1. That is the electron configuration for sodium, the longhand electron configuration for sodium. However, this is a filled sublevel. Since it's filled, it represents a noble gas. In fact, all of this represents neon. So instead of writing out 1s2 plus 2s2 plus 2p6 plus 3s1 all together, we can write neon 3s1. And that's a noble gas configuration where we replace the 1s2, 2s2, 2p6 with neon. So instead of writing all that out, we just write neon in brackets, and then we add the extra stuff on top of it, which we'll talk about here in a little bit. So that's the final configuration for neon. And that's a core configuration. So let's go ahead and try a couple. Let's talk about carbon. Carbon is right here. Okay. So what this means is that we had to go through hydrogen and helium, and that was the last filled principal energy level. Okay? The last filled principal energy level before carbon, which means that's the first part, the core part of my carbon configuration. Now I have to go through the S block. So I'll use the last S configuration, which is 2s2. Then carbon is 2p2. I know this because, once again, it's in the P block, it's in the second column, and it's in the second row. So that's where that 2 and 2 come from. So that's the noble gas configuration for carbon. Okay? Now, I'm going to erase this for a second so we can do the next one. We're going to do magnesium. Magnesium is right here. Okay? So we know that the last thing is going to be 3s2. I know it's 3s2 because it's in the third period and it's in the second column. So it's in the second column of the S block. So it'll be S2. It's in the third period, so it'll be 3. Now, the last filled energy level before magnesium, okay, and the way I know it's a filled energy level is I look for the noble gas. The last noble gas before magnesium is neon. So that is my core, neon. And then magnesium is everything. Now I include everything on top of neon to get the electron configuration for magnesium. So 3s1, and then I end up at 3s2. So I don't go past 3s2. So, oh, that looks dumb. 3s2. And there's my shorthand electron configuration. You'll notice this is much, much easier than writing out 1s2, 2s2, 2p6, 3s2, or writing all that. So let's take a look at what happens when it's a noble gas that needs the shorthand configuration. Once again, I'm going to erase all this. Okay. Now, argon, we know, is a filled energy level. And you will be tempted to write argon and just be done with it. But that's not right. Okay? You can't it's not its own core. Okay? Instead, we do the same thing. We go back to what was the previous filled energy level. In this case, it's neon. So, neon. Then we just go through the next ones. So I go all the way through the S block. So I know I'm going to go 3s2 at least. I know it's 3s2 because it's in the third period, and I fill it up. Now, argon is in the P block. Okay, the P block. And it's in the sixth column of the P block. So we know that it'll be P6. It is in the third period, so we know it will be 3p6. Okay? Excellent. Now we get to this idea of valence electrons. When it comes to valence electrons, we have to remember that valence electrons are the outermost electrons. So you have this positively charged nucleus right there, okay? And there are neutrons in there, I'm just not going to draw them. Then you have these electrons floating in these rooms around the atom. And for convenience, we're going to use the Bohr model, just for convenience. Remember, we know the Bohr model is not entirely accurate, but just for convenience drawing, I'm going to use the Bohr model. Okay? This electron is furthest from the nucleus. Since it is furthest from the nucleus, it is the valence electron. Nucleus. For a second there, I forgot how to spell nucleus. Okay? That means it's the valence electron. Now here's the tricky part. Valence electrons are in the highest principal energy level. So they'll be in the S and P's of whatever configuration they have. They are in the highest energy levels of the atom. Typically S and P. Oh, that looks dumb. There we go, S and P. Typically, there are some exceptions. Usually in the transition metals, and it gets a little weird in there. Now, here is a key feature that I want you to recall. Elements with the same valence electron arrangement show very similar chemical behavior. So the same valence electrons mean similar chemical behavior. Now, things that have similar valence electrons are things like the alkali metals. Sodium is, give me a second to look at my periodic table. Sodium is neon 3s1. So it has one valence electron. It only has one valence electron in its highest energy level. That one underneath rubidium, cesium, there we go. Cesium is xenon 6s1. So it only has one valence electron in its highest energy level. Because these both have one valence electron in their highest energy level, they react very similarly, especially when you put them in water, they explode. There are several videos on the internet, just look for alkali metals in water. They're pretty cool. So when things in the same group typically have the same number of valence electrons, so that means things in the same group have similar properties, which is actually something we've talked about before. Okay, this may be a little hard to read or see, but one thing I want you to note is the number of valence electrons. Okay, if we look over here at the noble gases, there's 8 valence electrons, 2 in the S sublevel, 6 in the P sublevel, 2 in the S sublevel, 6 in the P sublevel. Okay, and they're smiley faces. That's why they're happy. Okay, that's why the noble gases are happy. That's actually not why they're happy. They are happy because they are filled sublevels and they are chemically stable. They have 8 valence electrons. And because they all have 8 valence electrons, they are all similar. They are all non-reactive. And the same is true if we go and look at the alkali metals. They are all S1. Okay, so they all have one valence electron. Okay. Now, there are some weird exceptions on the periodic table. When we get to the transition metals, which are these right here, remember that they can have various charges, various possible charges. That's because they have various possible valence electrons. Okay? I am never going to ask you how many valence electrons a transition metal has in first year high school, in first year basic chemistry. Okay? In college chemistry, in AP chemistry, in a second year chemistry course, you would probably ask that, but I'm not going to ask you that. It is enough to know that the transition metals have different valence electrons based on how the electrons are behaving. So they have different possible charges. Okay? The representative elements over here are not like that. Okay? Oxygen has 6, sulfur has 6, selenium has 6, tellurium has 6. Everything in this column has 6. Everything in this column has 7. Everything has 5, 4, 3, etc. Okay? It is good to know that if you can figure out what column of the periodic table an element is in, you can figure out how many valence electrons it has, which means we can figure out how it will behave chemically with other elements. Now, this brings us to the idea of atomic size. Okay? Atomic size is usually determined as atomic radius. Okay? And the radius is actually when we take two elements, okay? So let's say we have two nitrogens. Well, hold on, let me redraw that because this will make more sense when I. Okay, so we have two nitrogens bonded together, and the radius is half the distance of that bond length. Okay? That's the radius. And it's weird because it's usually calculated. It's not usually actually measured. It is measured in some cases, but it's usually calculated. But one thing I want you to notice is that the elements actually get smaller as we go to the right. Sorry, I do know my left from my right. And they usually get bigger as we go down. Now, the reason they get bigger as we go down is because we're adding principal energy levels. Okay, you're adding principal energy levels. So we're starting with lithium, which has 2 principal energy levels. Then we go to sodium, which has 3 principal energy levels, so it's naturally going to be bigger. Then we go to, I'm going to move that because that won't be close enough. Then we go to potassium, which has 4 principal energy levels. So it's naturally bigger as we go down. Now, it gets smaller to the right because there's increased attraction from protons. So increased attraction from protons makes the element smaller. Okay, fluorine has 9 protons, whereas beryllium only has 4 protons. So since I just realized you couldn't see that. Since fluorine has more, it has a greater attraction, which pulls them tighter. Okay, which makes them smaller. Okay. Now, general property because of atomic size, or as a result of atomic size, is metals tend to lose electrons to form positive ions which, if you recall, we call those cations. And nonmetals tend to gain electrons in order to form negative ions, which we call anions. We've talked about that before, but just in case you forgot. And this has to do with filling up their p orbital. If we look at sodium, okay, which has the electron configuration Ne3s1, it only has to lose one electron to get back to a filled sublevel. I'm going to change this to blue real quick. It only has to get rid of that one electron, and now its cloud looks like neon, which is stable. It looks like a noble gas, which is good because noble gases are stable and unreactive. On the other hand, I'm going to switch back to red. On the other hand, sulfur has an electron configuration of 3s2, 3p4. So it is too short of a noble gas. So what it does is it adds to so that it looks like the next noble gas, which is argon. Okay? So that it looks like neon 3s2 3p6, which is argon. And we have to show that it's -2, that it's got 2 extra charges, and I forgot to show that over here on neon. Neon should have or for sodium, it should have a +1 charge to show that it lost an electron. Okay? So the whole idea of gaining and losing electrons is that it becomes positively charged, is that it becomes electrically stable, so that it looks like a noble gas. That's the whole goal. Now, this goes into how easily does an element gain or lose an electron from its configuration. Okay? Some elements gain and lose more easily. Let me change this back to red. This losing an electron is called ionization energy. Or it's called ionizing. Sorry, let's do that. We'll talk about ionization energy here in a second. Okay? And this is actually down a column. Lithium is at the top of the column, then it's sodium, potassium, rubidium, and cesium. So it gets easier. It would help if I spelled words correctly. Easier to lose an electron as we go down a column. And that has to do with its size. The bigger the element gets, the weaker the attraction between the valence electrons and the nucleus. So, bigger elements, or bigger atoms, let's say that. Bigger atoms have weaker attraction. Yes. To valence electrons. Okay. So this kind of also indicates that elements in the same column are similar, but not identical. So all the alkali metals that we've got listed here, lithium, sodium, potassium, rubidium, cesium, all of those easily lose electrons, but some of them lose electrons more easily than others. So this indicates that not all alkali metals are created equally. Okay, so ionization energy, if we go back to that idea of losing an electron, ionization energy is the energy required to remove an electron, or to, well, yes, remove an electron from an atom. Okay, so this is just a basic little chart to help us remember. Ionization energy decreases, meaning it's easier. Okay, basically it costs less energy. Okay, the cost energy goes down to remove an electron, whereas when we go across a period, the energy required to remove an electron increases. So the energy cost goes up as we go left to right on a column. Okay, and this has to do with atomic distance. Remember that our atoms get smaller as we go left to right on the periodic table, and since they're getting smaller, their attraction is greater, so they're holding on tighter. So it requires more energy to remove a valence electron. Okay, just for a couple of practices, let's figure out the valence electron configuration of calcium. Now, if we want to do this, the old-fashioned way, okay, we've got our 1s, 2s, 2p, 3s, 3p, 3d, etc. And when I look at the periodic table, calcium is in the 4s block. So that's as far as I need to go. Okay. But it's asking for the valence electron configuration, or noble gas configuration. So I need my noble gas in parentheses. So I have to ask myself, what is the noble gas that is before calcium? Well, the noble gas before calcium, according to the periodic table, is argon. Okay? So that's the first part of my configuration, is argon. Now, argon takes me up to 3p, and it's full, so 6. Now, you might be thinking, well, how many electrons does that mean? How many electrons has it already used up? Well, what's the atomic number of argon? Hold on a sec, I'm going to look. My periodic table's across the room. 18. Argon is 18 electrons. So I have 2 more to deal with. So if it's 3p6, the next one is 4s. So 4s, I have 2 left, and how many can the 4s level hold? 2. Which makes sense because calcium is in the s block, and it's in the second column of the s block. So this is my valence electron configuration for calcium. Now, our valence electron configuration for tritium. Okay, it has 39 valence electrons. Tritium is a transition metal, but it's what I would call a normal metal. So it doesn't follow, it's not an exception to any rules. It's not a special, I mean it's special because all elements are special. But it doesn't break any rules. So what we do is we know the noble gas before tritium. Since we're looking for the valence configuration, we're going to look for the noble gas before tritium. The noble gas before tritium is krypton, which accounts for 36 electrons. which means I have 3 more left. Now tritium is in the D block. It's in the first column of the D block. It is in the 5th period. These two things mean the last part of its configuration is going to be 4D1. So now it comes down to figuring out what's in the middle there. Well, when we look at our periodic table, we notice that I have to go through the S block in the 5th period. So since I'm going through the S block, I know that it's going to be filled. Now to determine which S block it is. Well, since it's in the 5th period, it is the 5th S block. Okay? And that accounts for my 3 extra electrons left over. So that is my valence configuration for tritium. Now, which would you expect to have the highest ionization energy? Okay? Barium, strontium, or calcium. So let's look at these. First, we have to find these on the periodic table. And these are all alkali earth metals, meaning they are all in group 2. And I'm going to go ahead and write them in the order in which they appear in group 2. They appear as calcium, strontium, and barium. Now we know that ionization energy, the cost, decreases as we go down. So it decreases as we go down a column. So, I can't believe I wrote that so well. Sorry, just marveling. So that means that the one that has the most would be the one that's closest to the top, which is calcium. Okay, and then our last note is arrange the following sets of elements in order of increasing atomic size. So I have to find these on the periodic table. Give me a second. I know I should have had this done already, but I forgot. Okay, so I've got antimony, xenon, rubidium, and tin, xenon, rubidium, and strontium. And all of these are in the same row. They're in the same period. They are in the 5th period. Since they are all in the 5th period, I'm going to write them in the order in which they appear in the period. So they appear as rubidium, then strontium, then tin, then xenon. Since they appear in that order, I know that elements get smaller as we go from left to right. So they decrease in size. Since they decrease in size, that means that xenon is smallest, but rubidium is largest. So to put them in order of increasing size, we have to go xenon, tin, strontium, and rubidium. And that's our final answer. Now, if you have any questions, feel free to comment, feel free to ask, feel free to